People don't know, but it used to be the student room.
I know that. You got
I use that. Anyway, so I want to talk about some work which is ongoing with Sunil, Mukhi and Wu. Zhejiang is a student at Beijing University and he is going to MIT in a few months as a postdoc. And Sunil Mukhi everyone knows. And actually it's funny because half the work I've done with Zhejiang last summer and the other half sort of being done with Samir, and we'll have to, it's still not all put together. So, so it's a bit preliminary, but there are enough details that I hope it will be interesting. Other caveat is it's very technical and it might be a bit dry, but anyway. So, the context is to study von Neumann entanglement in 2D CFT. And we don't want to specify right here which 2D CFT, but just to ask whether standard calculational methods for this are actually adequate or not. And probably you know that the methods in question have been pioneered mostly by Cardi and Calabrese in a series of papers over the 2000s. And it turns out that there are some subtleties which we might have uncovered, and that's what I want to talk about today. So the question here will be the spatial entanglement between the degrees of freedom in a single interval and the complement of that interval in a 1D space. And there's also the multi-interval question, which is complicated, and that's that will be an additional complication over what I'm doing, so at least today we won't bring it up. Now, this quantity has a, so I'll define them everything in a minute. This entanglement entropy has the property that at zero temperature, and if the 1D space of the CFT is infinite, then it's simple and universal, the answer. Depends in fact only on the central charge of the CFT and on the length of the entangling interval relative to the length of the total space. So, when the space is infinite, you should imagine that I just have an interval of length L, or if the space is compact, then you should imagine again I have an interval of length L, but the whole thing is of length capital L. So this is the infinite case, this is the finite case that I have. Now it's also, this universality property is also true if the temperature is zero, even if we are in this situation where the space is finite. This actually complicates the calculation because periodicity sort of means that modes here are connected to everything on both sides, while somehow the infinite thing is somehow simpler. But as long as temperature is zero, then it's still universal. On the other hand, if temperature is finite, but the space is infinite, then also it's universal, and I'll show you the formula for that. So that, of course, for the mathematically inclined, suggests that why don't we consider finite temperature and compact space. So the space looks like this, and the temperature is finite. And then the answer is non-universal and relatively little is known. So this is a fun place to do calculations, and is the case that I'll discuss here.
So sir,
yes.
This quantity is simple and universal for Renyi entropy, even for taking the Q equals 1 limit?
Yes, even for Renyi entropy. I'm not sure if I have that formula, but it's simply the exponential. So there's a certain, I'll show you, I'll just show you the formula and maybe I'll, thank you, because I think if it's not in the slide, I should put it in the slide for future. Okay, so the more detailed statement is that we partition the 1D space into an interval of length L and the rest, and then this interval is called A and everything else is called B. And what we do is we trace out the degrees of freedom in B, and we are left with a density matrix on A, and that density matrix then we want to insert in the formula for entanglement or any entropies. So the entanglement of von Neumann entropy is then obtained in this way. So we trace out rho over B, we get rho A, and then we put rho A into this von Neumann formula, and we get the entanglement entropy that we want. Now there's a little technical caveat, which is that people in this field complain that you shouldn't call this entanglement entropy, because it is really an entanglement measure only if rho is a pure state. If rho is not a pure state, it's still the von Neumann entropy, but it doesn't happen to be a good entanglement measure. because it's then contaminated by whatever is not pure in the original state. So it's not a measure only of entanglement, but of entanglement and some other things. However, there's an interesting thing called entanglement negativity, which is sort of our next goal, which is a good measure of entanglement even for mixed states. So entanglement negativity somehow is the next thing. And as you can imagine, Cardi and people already have some papers on that. Now, in practice, this log messes up this calculation, and so we prefer to do this calculation where we calculate an n-dependent quantity for some integer n, positive integer, by taking the trace of rho to the n. So this process of taking the trace of a density matrix to the n is relatively simple, or at least easy to define calculation. After we are done with that, we take the log, then it's no problem. It's the log of rho which is difficult, not log of trace of something. And then, of course, we get this, and that's fine. This is called the Renyi entropy. But then we take a limit, n goes to 1, and in that limit, it's a singular limit because 0 by 0, but if you do it carefully, it just comes to that. And so you have to do this, and then imagine continuing n from positive integer to 1 plus epsilon and take epsilon to 1. Now, one more caveat is that I will make no attempt to do that part in this talk. So it's really not going to be a talk about entanglement of von Neumann entropy, but only about Renyi entropy. Somehow that step of taking n goes to 1, it's always been a weak point of this subject, because you're calculating for integer n and then somehow you have to guess. But it's particularly weak point when you're dealing with the fact that n is the genus of a higher genus Riemann surface, because no one really knows what is a 1 plus epsilon genus surface. But if we could know, then it would be something useful for this.
So just to understand that there are additional subtleties when you do your case where both directions are
Exactly.
taking the end.
And it's not even a subtlety, it's just the fact that we get things like products of theta functions or product arguments, and one doesn't have the slightest clue from that, how to go from that to a continuous value of n. Because that actually nobody's ever attempted as far as I know. So here are the results. T equals 0 and infinite space, the famous answer C by P log L by A. I think this is Halsey, Larsen and Wilczek in a very...
Halsey's PhD thesis before he went out of physics.
Out of business, yeah, I thought so, because never heard of him again. But in fact, marvelous result, and obviously it predated all the excitement by a lot. I don't know if you were around.
I was very much around.
You were around then, so do you have some idea what they were thinking about or why they were thinking about this?
It was 2D black holes, and everyone wants to understand the information puzzle. So you first want to say,
but this, I see.
What's the density matrix or entanglement outside
the black hole? But this was before or after all this Sorkin and Srednicki papers, which tried to make
Srednicki is nearly contemporary, yes.
Sorkin was definitely earlier. They were the ones who really tried to do this.
Was earlier. But I think Halsey first and then Srednicki.
Okay.
But this was all way before 2004. And in fact, this development seems to have sort of sprouted independently. And around 2005 or 6, Cardi says that I think much of this is already known in the.
I see.
Yeah, there was a huge. There was this paper. If I may say, we had an alternate derivation, slightly different, in the paper with Prescott, Strominger, and so on. So there was all of that. Then it died. Then Cardi released it.
Then Cardi released it. Right.
Sorry.
So this is the universal formula, and curly L is the length of this interval. There is no capital L because this is at infinite capital L. Okay, so that's the formula. And there's a UV cutoff. These are all standard kind. Good. So this formula becomes more interesting when the interval is like this lower case where there's a capital L, because then you need periodicity, and in fact you get sine of pi L by L, and then this factor, and then log of that. And it's very easy to take the limit L goes to infinity, in which you get back the previous expression. So this is the formula for von Neumann entropy. So again, as you asked, if we do this, if I just bothered, I could write the Renyi entropy as well in the same terms. On the other hand, if we work at temperature, which is beta inverse and non-zero, Then we have the original density matrix is thermal, but then I keep L infinity. So I'm in this case at finite temperature, and that's the formula. Someone, I think Chris Herzog told me recently that Korepin was or claims to be the originator of this and is extremely mad that nobody cites him. So that's the data point you should keep in mind. There is a paper of his which does have this. And of course you shouldn't be too surprised because in both cases the total space is a cylinder and path integral really doesn't care which way you orient your cylinder, whether the compact direction is time or the compact direction is space. And so you expect some relation. This is a warning that I already gave, that this von Neumann entropy is not a good entanglement measure in this case. It's not a monotone and all that. But it's still interesting and it's a starting point to study more interesting things like relativity. Yes.
So in both cases, the original manifold is a cylinder.
Yes.
But once you put the cuts into the replica, it won't be it will be different, right?
Yeah. No, it's still the same though. I mean, it's a glued cylinder. Now, of course, the cuts, you could argue the cuts are in different directions.
Yeah.
And that's certainly true. But geometrically, if you think of the cut as being just a complex number on the cylinder, you can just take a complex interval, oriented whichever way you like. Then mathematically it's the same, except that in one case you have to restrict to real and in the other case purely imaginary. Which is in fact my next statement, that these formulae are interchanged under the modular transformation. Beta goes to L, inverse temperature to the spatial size, and L goes to IL.
If I look at the whole manifold in which, suppose I'm doing the Renyi entropy with n copies.
Yes.
I look at the whole manifold, that's topologically the sphere in either case, right?
In this case, it's topologically the sphere in either case. Yes.
And that's why the answer depends only on the central charge. So
That's correct. That's exactly right. Okay. And so this modular behavior is because the path integral treats temperature as Euclidean time and it doesn't distinguish between compact space and compact time. Now, the case of interest to us is finite temperature and also finite spatial size. And now we are on a torus of modular parameter tau equals I beta by L. And as everyone likes to do, we just imagine tau is complex with positive imaginary part and then we can always restrict to this case at the end of everything. And there's a nice result due to Cardi and Herzog, which finds the universal thermal correction to the Renyi and von Neumann entropies at lowest order in e to the 2 pi I tau, which is basically a low temperature expansion because beta is large, for an arbitrary CFT. And here they show very precisely that this answer must violate that universality because the first correction involves q to the delta, where delta is the conformal dimension of the lowest non-trivial primary and f is some function which they compute. And so now the dependence is not only on C but also on delta, which is conformal dimension. So that's more data about the CFT. Yes.
and now if you take the Renyi entropy with n copies, what is the topology of the?
Yeah, we'll do that in a moment. So that's the subject of the entire subject. So we'll be doing that in a second. But anyway, this is just to show the non-universality. Actually, their calculation came after one by Takayanagi and collaborators, who anyway calculated the case of finite temperature and finite size for free fermions, and that's a result which I'll be commenting. Okay, so that's in fact this statement. It's only been carried out for free theories, but at least free fermions are interesting free theories. Free scalar is also on a compact circle is also an interesting free theory. So those are the cases that are known. In the scalar case, it was done first by Justin and student Shavik Datta, but there were some things not right about their answer, and it was later corrected by Jeja and Wu, my collaborator, and Bing Chen. And there are some puzzles which appear to be more or less conceptual in such a just what seems to be a very technical issue. So let's get down to that.
So just to make one point is that so if the finite size has a boundary condition rather than something like that, then one can think of this as through the method of images.
Yes.
So you have two twist operators here,
Yes.
and you have two twist operators there, so it becomes a 4-point function.
Right.
So this is the usual non-universality of the 4-point function.
Good. Thank you. That's a good way of seeing it. But even with the compact cylinder, you can think of method of images, except there are infinitely many images. So in some sense, yes, non-universality, again, it's just the fact that multi-point functions are not.
And sorry, you'll surely come to this, but when you're compactifying even one direction, but perhaps both of them, you then have the choice of various kinds of boundary
Yeah, we
conditions
come to
and
that.
so on. So
Yeah.
it's a rich structure
For fermions.
for formulas.
Okay, so the calculational procedure, so let me show you the picture, is that trace of root to the n is something called the replica partition function Zn divided by the ordinary partition function to the nth power. And since Z1 is assumed known, it's just the torus partition function of a CFT. If you know the CFT, you ought to know Z1, at least, well, if it's a rational CFT, if it's really one of these fancy orbifold CFTs that we use in string theory, then I don't know how well one knows Z1. But anyway, it's the least you need to know. Anyway, if you calculate Z1, then from that you can get, if you calculate Zn, then you can get Z1 from that. So the calculation reduces to calculating Zn. And for that we do this. So this is the torus, opposite sides identified, and we attach them along this interval. And this is Shiraz's question. So this has genus 1 and this combination has genus n. And the interesting thing is that this attachment doesn't add any new handles, it just attaches handles to each other. And this is different from the case considered by Cardi et al., where you had not a torus but let's say a plane with multi-cuts. If you have multi-cuts and then start joining them to replicas, then new handles form when you join. In fact, that's the only way new handles form, because let's say you start on a plane, no handles, but now I have two cuts and I join them to the next guy, I get one handle. So I get genus n minus 1 for n such copies. And of course, not surprisingly, that's how I think Riemann discovered Riemann surfaces. So they're branched covers of the plane, where the plane is glued along cuts. So this is not a surprise. But here we are doing something which is simple conceptually, but nobody seems to have actually worked on this in much detail, and that's probably why we found something new, which is to take an existing Riemann surface, the torus, and then just glue it along a single cut. So this is the case of interest. So the branched cover has genus n.
And I mean, sorry to be so dumb, but
Please.
just to be sure that I understand why it is genus n, I mean the A, you get n A cycles just going around each other. I mean, what have you have
Actually,
one sort of cycle.
One of the funny things is that all the A cycles and B cycles are just the old A cycles and B cycles of each copy of the torus.
Oh.
So in other words, if you ask what's the cycle around this, it's a combination of the A and B cycles on this. You see, if you do A, B, A inverse, B inverse, then you normally get a trivial cycle on a torus, but now it becomes the cycle wrapping the cut. So it's linked to the same combination of the next guy. But A, B are still cycles. So in fact, this Riemann surface allows you to choose cycles which don't have any reference to the cut. Again, a big difference from the multi-cut case, where the cycles have to go around the cut in order to be cycles. And that actually greatly simplifies this calculation.
So the n A and B cycles are the A and B cycles of the n copies. And okay, and then I see. Interesting. And then these relations link them all together. Okay, interesting.
Okay, so the replicated torus manifestly has genus n. And now one nice thing, though it's not often said in the literature, it's sort of implicitly used by some people, particularly Schnitzer and so on, which is that now you can just calculate the genus G partition function. Nobody obliges you to bring in twist fields and everything. Somehow there's a feeling that replica trick and twist fields are the same thing. They're not the same thing. You've got a surface. If you're smart enough to calculate its genus G partition function, which you might find in some paper of Greg Moore, who was trying to do it for the bosonic string in those days, or somebody, then you're done. Berlin days famously, Alvarez, Gaume, Moore, Waffa, all that series of higher genus calculations. If you find the answer there, you don't need anything else, conceptually. And this is a comment which, it seemed obvious to me, but I never found it in the entanglement literature, which always had this obsession that you have to now do something to this. So you don't need to do anything. What you need is to find the period matrix of that surface which I drew.
And
now,
then the Liouville action as well. all flat.
Yeah, it's all flat actually. But yes.
I mean, the full answer will not depend just on the complex structure. It also depends. Oh, but yeah, right. It also depends on the if you take this and put your metric in a standard form.
Yes, that's true. That's correct.
There's a a while factor.
That's actually correct.
And
Thank
you would need the Liouville action for that transformation.
Yeah. And I think the reason we don't in this case is that though this surface is singular, it's also flat.
Yeah, probably.
It's a singular and flat limit, and you can see that. You know that a genus G surface on average has to have negative curvature. But then look at this one. This is just made up of completely flat tori, and they're all glued. And so the curvature must be averaging out over those points. But that's it. So it's a singular surface, but it's flat.
You see, although, I mean, I agree with Shiraz in that, as you say, even for the simple case where you don't have two non-trivial cycles, you could do the calculation without recourse to twist fields in the dimension, but just by keeping track of the metric and the Liouville factor, by smoothing out the metric near the singularities and keeping track.
And going to a standard form.
Going to a standard form, and in that way of doing it, the whole thing comes from our box inverse suitably.
Yes, okay, thank you.
Yeah, so I mean, so just to say, you have to be careful that when you quote some result for the partition function, that result is quoted in this metric.
Yes, but
If it's
now
quoted in
what's puzzling me now is that the result we actually took was from a paper of basically it was Alvarez, Government, Moore, Buff. Actually, it's not even any of those. It's Krishnik's old paper.
But you know, there's a standard metric which is that of constant negative
Yes.
curvature.
Yes.
If they quoted in that metric,
Good.
there would be an extra additional Liouville factor
Yes,
between this and
yes,
that.
I agree. Okay, thank you. This is something I should look into. We haven't thought perhaps too carefully about that. Okay. Now, this is probably also related to another fact, which is that the genus G partition function has a dimension unlike the genus-1 partition function, because it's a section of a non-trivial bundle, which I think is the same roughly as what you're saying. Anyway, so supposing we knew the genus G partition function with these caveats, we would have something that depends on a period matrix omega AP, which is very general. You know that period matrix parameterizes the Riemann surface, and actually it's so general that some period matrices don't even describe a Riemann surface, only some family of them do. But in this case, the question is, can I find the period matrix of the surface I drew as a function of the modular parameter of the original torus and the size of the entangling interval, because that's the only data that this figure contains. L is that thing, capital L, here we have scaled it to 1, so we get L by capital L, and then each of these tori is identical and has tau, so it's actually a very symmetric genus G Riemann surface, and it has some omega which depends on these things. So supposing I know that, then I should be able to write down the partition function. And then of course the genus of the surface should be set to n, the number of replicas, and we find that. Okay.
Really sorry for asking this remedial question, but the period matrix again tells you how things transform under generalized modular transformation.
Yes, except that here we don't want to make generalized modular transformations, because the generalized one would mess up so the only ones we're interested in are SL2Z on the first torus and the same on all the tori somehow. So we are in a very, so this is the whole idea, it's a replica surface, it's not just any Riemann surface. But some of the properties of a general surface will of course descend to the replica case as a special case. Okay. Now here's the other, often more convenient way to compute Zn that works quite well for free theories. And here the idea is that imagine I have a path integral representation, and phi tilde is a free field which lives on the kth replica, and the statement that these are glued on the branch cut means that if I took phi tilde k through the branch cut, it would land on the next surface and it would become phi tilde k plus 1. Now you can take a linear combination of these phi tildes. So I anticipated we would do that so that the result are called phi's with this phase, and the idea here is to diagonalize this. So this kind of monodromy, if you think, is the shift matrix, the matrix which is all zeros and then all ones off the diagonal, so that each guy goes to the next one. But of course we know that that's diagonalized by, I think the other one is called the clock matrix, which is basically these numbers. So therefore, after we do this linear combination, then the new guys go to a phase times themselves as we go through the cut. And now the idea is that we then forget about the replica surface, we work only on one torus, but it has many fields, n different fields on it, each one with a different monodromy parameterized by k. And k starts from 0, so here k goes from 0 to n minus 1. So one of them is the actual sum of all the phi's, which is obviously invariant, and then the other is the sum with one phase, then they pick up a phase, then some with double the phase, they pick up double the phase, like that.
There's a monodromy going around any branch point.
There is a monodromy going through the cut. Yeah,
Yes.
through
And
either
then-
of the branch
But
points.
there's another one.
Yeah,
so the
but
other
that,
one, and they meet up somehow.
yeah, they meet up because it's again it's a torus.
I-
So
What do you mean the other one? When you have a branch, you have one branch cut,
yeah.
and then you
So
go
we have this
across
branch cut. So if I go like this, in this direction I go up. Conversely, if I go like this,
Oh, you
I
go
also
down,
go up.
yes.
But if I go like this, then I don't go.
Yeah, yeah.
So these 5K, these fictional 5K fields have these periodicities around both these points.
Around both the points, exactly. And then the idea is very simple. Let's insert a field here and here at those points, which is non-local relative to the phi's, so that the OPA of those fields with the phi's induces this behavior, and then we calculate the correlation function of those fields. So that's the twist field idea. So this phase can be associated to the presence of a twist field, one at each end. So in fact, sigma and sigma dagger, which sort of cancel each other's monodromy out. And so if you go between them, then this OP takes care of the non-locality that you want. And there's a very simple and nice theorem. And again, I realized that many of these things date back to Krishnik's work. Actually, the whole twist field construction dates back to that. In a sense, actually, he wrote this very short paper in physics letter or something. He died very young, I guess people know that. And then all this Alvarez, Gaume, Moore, Rafa, Berlin-Days did a lot of stuff, but somehow the nugget was an important part of that ideology was all there. Okay. So then the replica trick says, take this, and these 2-point functions are all normalized by Z1, so there are n of those, so you get the final answer by just taking these 2-point functions. Or you can get the numerator by taking unnormalized 2-point functions. And these 2-point functions, if you know some construction of the twist field, then you can look up torus 2-point functions, which are quite well studied. Okay, so now in what follows, I'm just going to write this ratio of this length over the full thing as a complex variable Z12, and because now we are going to just do some mathematics of this. So it's just important to remember that Z12 is a number between 0 and 1 sort of, which parameterizes the length of the entanglement.
Just
Yeah,
confused with something.
sure.
If you do trace rho to the n, you don't take the 2-point function of the twist n field, is it? You take the product over, I thought you just, because the
No, it's
twist
this,
n,
yeah, it's this
K-
n-fold product which is sometimes called the twist field.
Yeah,
You know,
sometimes so product over k, which goes from 0 to n minus 1. So you could say that product of sigma k from 0 to n minus 1 is the twist field. But the point is that each factor is made out of only the corresponding fundamental field.
Yeah.
So each twist field twists only its given partner fundamental field and is local with respect to all the others. So basically, let's say if you had n free boson, if you had one free boson or one free fermion, now you have n of them, effectively, in the calculation.
Why does this work only for free fields?
Well, yeah, perhaps, so this is something I kept worrying about. I've never seen it applied to non-free fields. I guess the problem is that if you had interactions in the path integral, then this process would mess up everything quite badly. So it's not
So these
clear.
5Ks would interact with each
So
other.
the 5Ks would interact with each other. Yeah. So the fact that these are independent because they each live on a replica, but the new 5Ks are still independent because it's free fields.
No, but I mean, they could, on each sheet, they could be interacting objects. But this particular
No,
linear
which ones?
combination-
These could be, right? These are the original fields. So
Yeah.
they interact with each other on each sheet,
Right.
but not with the guy on the next sheet. But now when I take a linear combination of them, then this one interacts with, now everybody's on one sheet, these phi's, but they all interact with each other. It's not n decoupled CFTs. While this calculate, so okay, you could do it. Somebody should try doing it.
Each CFT could be some non-trivial fixed point or
Exactly,
some exact
exactly.
CFT.
Yes, yes.
So as a result, this construction that you have done, including the construction of the twist operator, that would go through again.
Well, the point is, if it's a non-trivial fixed point, it means there's some non-linear interactions in the Lagrangian, right?
I mean, these are just primary fields of that particular CFT, and you have to invent some.
Okay, I guess the confusion is not really that these are primaries, no? This is all a statement about path integral calculation.
Yeah, I agree.
So there has to be some fundamental field, which is the field in the Lagrangian. That's actually somehow the most confusing part. Everything operatorily we have defined it as Zn over Z1 to the end. That's the end of that discussion. Now we have to move to a path integral description.
Yeah, I mean,
now it depends whether it's a free or not free path integral.
I mean, maybe this is not particular, but the way Cardi and Calabrese introduced the twist field is to do it somewhat differently. Let's look at the one-point function of the stress tensor
Yes,
in this
yes.
complicated ring.
That's true. That's that's uniform. So that's another step which I'm not using.
Yeah.
That's not how they introduce the twist field. Once they get the twist field, instead of opening Di Francesco's book and asking what are the correlation functions of that twist field, they use uniformization because they are working in a system which is not this one, not this Riemann surface. So their Riemann surface is basically a plane. The point is, a plane or a cylinder you can do a lot by conformally mapping it to something simpler, and they use the conformal anomaly to extract the twist field correlation function. In fact, they use that actually to even prove this theorem.
That's fair. I mean,
so I'm assuming that's all been done in the same theory on the plane. But now if we are on the torus and we try to do, there we can't use uniformization. But we can still imagine using this diagonalization trick. In fact, this is what was used by Taka and Agi et al. For this.
I still think that free field is not necessary. I mean, for this, because I mean, you could say that, okay, this is my one-point function of the stress tensor, and therefore, I can, okay, it's postulating the existence of some.
See, if it's not, as I said, if free field is not necessary to do this step, or this step, to say that there are twist fields and they have these dimensions, for that you don't need free fields. That is what Cardi and Calabrese already did.
Yes.
But now I want to use this diagonalization procedure to calculate the twist field correlation functions on a non-trivial space without using any uniformization, because you can't uniformize a genus G surface into something different.
Okay, got it.
And then I think it only works for free fields, or of course these phi k's will be coupled with each other, which as I said is worth looking at, but seems quite.
But just to say, the end of uniformization might be to take this genus G surface to a genus G surface in a particular metric.
Yes, that I agree.
So, and then, as you said, look up correlators,
Yes.
just partition functions
Yes.
of
Yes.
that genus G surface in that metric.
Yes.
That might be a close analogy.
So that implicitly we have done.
I see.
What we might, I think we might have done what you are saying,
Yeah.
but I think I need to think about this
Yeah.
point more. It's important. Good. So now, with all this, I can highlight that there are two ways to compute the same answer, namely the Renyi entropy. One is write the genus G partition function after finding this period matrix omega in terms of the data of your problem and evaluate it on that, and that's it. The other is do what I've said here and compute the genus-n correlation function of twist fields. And if both can be performed, then they should agree, because there is no visible reason why these two methods should not both work, particularly in things like free fields.
And the second method would be for free fields.
The second method would be for free fields. The first method, in principle also, you can hope for the best, but again, it probably works for free fields.
Somebody very strong who can do higher-genus CFT.
Higher-genus CFT. So there are papers on things like higher-genus partition function of minimal models. But I strongly suspect that even minimal models are in some sense free field theories in this Coulomb gas description. So I don't know really which very non-trivial CFT can be done that way. The actual results are a little surprising. Anyway, so that's just a preview. So let me now focus from now on till the end on free fermion CFT. We'll just use one free fermion, one Majorana fermion, central charge half. Of course, the CFT of that which we know and love is the Ising model. But there's a subtlety, there's a free fermion theory and there's the Ising model, and one is equivalent to the other only if you do one circuitous step of having the spin field introduced. Otherwise, they're not equivalent. And that has to do with the
GSO projection.
GSO projection, spin structure, however you call it. Okay. Anyway, so we looked at this and we found the following. If you ask for the answer in the first method, you get some universal factor f, which I'll be writing down soon, times a function of z1, 2 and tau. We've called it L. This is unimaginative. This is L and R stands for left and right of some equation we are going to write. But L is determined in terms of higher-genus Siegel theta functions, because that's what fermion partition function looks like in higher-genus. In fact, as you probably know, theta functions in retrospect could have been invented just to describe free fermions on a Riemann surface. That's the whole. They just naturally carry in fact, their mode expansion is the mode expansion of free fermions, and they come in exactly the variety of characteristics, which is the number of fermion boundary conditions around each handle. And their characteristics alpha and beta are nothing but 0 and 1. Or yes.
Gil Spark in his lectures of conformal data has this line saying, you might wonder how did Jacobi and friends get it all right, including the minus c by 24 they didn't know about from.
Exactly the point. No, it's right. Actually, I think that must have been a real thrill, finding the physics behind some ancient mathematics. Of course, the other famous case was Polchinski finding this Jacobi's abstruse identity. That's the cancellation of the tadpole in superstrings if you do it in the open string channel. And it's Jacobi's equatio identica satis abstrusa, which means identity whose meaning is abstruse. It turns out to mean deep brains, but how did Jacobi know that? Deep brains and supersymmetry. Okay, so likewise, the second line is the same factor, so therefore when we compare these we can cancel off, it's just some part which comes out the same, times r in terms of genus-1 Jacobi theta functions.
And Z1 goes even to your scale length of the
entangling interval. So it's this ratio of this L over that. It's just, tau is the modular parameter of the original torus, and both sides depend on the number of replicas, because we are trying to calculate something for a fixed genus or fixed number of replicas. So in the first case that's fixed genus, in the second case that's fixed number of twist figs. Okay, and just to say the calculation of Takayanagi et al. Was already done, so we have not improved on that, we've just taken that for the second line. Yes.
So in order to satisfy Shiraz, you would have to take one and you would take the particular degeneration limit in which it becomes the replica surface.
Yes. Yes. No, so one is the answer after doing that. It depends only Z1 on Z1, 2 and tau.
And that's a unique characterization of the period matrix in terms of what you're...
Yes, that we'll see in a moment. Period matrix is not the problem.
Yeah,
The problem is that there's an overall additional factor which somehow I have to figure out now why we don't need it. But I have a strong feeling that it comes from the fact that this surface is sort of flat.
Yeah, I mean what I mean is that the legal part can be thought of as a different choice of G hat.
Yes, that's right.
There's a difference.
Yeah.
But that's not in the complex structure.
That's not the
Yeah.
okay, exactly. So the omega AB
This
is
is the orthogonal part of the complex.
omega AB is
Okay, so the conjecture that these two methods agree amounts to that these factors agree as long as we take out some common factors which we can, and then we can have some sharp identity which we can test, and that's the point of this. So this is the stage more or less at which we were last summer when I was in Kyoto, and this thing lingered for a long time because then we couldn't find easy ways to test L equals R, though we had written it down, and this is where Sunil has been invaluable because in fact what we discovered last summer, the last thing we managed to do was to show that L and R are Jacobi forms, and so we decided to look for the world expert on Jacobi forms, who fortunately showed up in December, and that's how things continued. Okay, what we we'll see is that the two sides seem to agree in a power series expansion in the interval length. However, they don't seem to agree as exact functions for some reason which we are quite baffled by. So this is preliminary and it's only been a few
The
weeks.
power series breaks down after a while.
Yes, and we'll see also that it breaks down outside the physical region, but in a region where the functions are well defined. It breaks down when Z12 is greater than 1. Now Z12 is not supposed to be greater than 1 because it's L over L, but the mathematical identity allows for a Z12 which is greater than 1, and there it doesn't seem to hold. So that's a puzzle. I don't know how important the puzzle is, but it's a
So, but if you were interested in your original question of the Renyi entropy,
Yes.
then you calculate either way and you would get the same answer because you'd be restricted to Z12 less than.
Well, so again, if it breaks down for Z12 greater than 1, it could be still true for all Z12 less than 1, or it could be true only in a power series sense, and there could be some non-perturbative corrections, or we don't know exactly what's happening. Samir keeps mumbling instant on corrections, but I don't know what that
I
means
see.
in this case.
So, okay, so I see, I see.
So we don't know. So let's see the thing, and then maybe, and so one purpose of giving this talk obviously is that we may have some solutions. Okay, now there's another subtlety, which is that both L and R are spin structure dependent, so you might ask what it means to compare them, given that the L side computed in higher-genus has 2 to the 2n possible spin structures corresponding to that number of handles, but R is computed in genus-1 where there are only 4 spin structures. 0, 0, 0, half, half 0 and half, half, or plus, 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 minus, 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 like that. So how do you even start to compare them? And this brings up a problem which already was highlighted 2 years ago, and I might have spoken about it here. So in 2014, Sagar Lokhande and I wrote a paper where we pointed out that if you just sum over these 4, so we just took Takayanagi's calculation and tried to sum it over spin structures to see if it makes sense potentially to describe, say, the icing model Renyi entropy. And we found a modular invariant answer, but it doesn't satisfy the so-called thermal entropy relation, which I'll summarize in a moment. And so that's been a puzzle. However, as we'll see, summing over all, this should be 2 to the 2n spin structures of L, leads to an answer that does satisfy the thermal entropy relation. So here we have an interesting situation. It's not that L can be equal to R. L can be equal to R only for a few choices out of these 2 to the 2n spin structures, if at all it's equal. But if we really want to get the Renyi entropy in a modular invariant form, we need to sum over all independent spin structures in higher genus.
So which,
Yes.
so which was L and which was R?
L was higher genus and R was genus-1. Twist field.
R for genus-1 being n copies.
N copies.
Yeah, but Sunil, I thought the way you set it up, since you told us that in the genus-n surface, the A and B cycles are basically the A and B cycles of the genus-1
Yes.
surface.
Yes.
I would have thought once you choose your spin structure on the genus-1,
Yeah.
then just that
Yeah, would have thought
determines it.
so. And that's why if this had given a positive answer, we'd have just gone home and not thought of the genus-n case. But I'll show you why this happens. It will become clear when I show some formula.
And your point is, if I chose that particular set of boundary conditions for
Yeah.
the L part, the
Yes.
genus-n case, the answer is
If I sum over all choices, actually maybe I'll answer
No,
your
but-
question right here on the board. See, the issue seems to be like this. The issue is that I have these toroid due with a cut.
right.
Now, just thinking intuitively, how does the spin structure of one influence the spin structure of the next? And the answer is, supposing the cut is very small, almost not there. These are decoupled toroid. In that case, intuitively, there is no reason to think that the spin structures are the same. Okay. On the other hand, supposing the cut is as large as it can be, in this limit, this whole thing is one torus which is n times as high. You see that? Because then I can put the cut here and glue it to the base here, glue this to this, and the whole thing piles up into a torus like that. Those modular parameters are there. But now that n copy torus has only one set of torus spin structures.
Yeah. But I'm just thinking in terms of the original problem of entanglement, if you think of why the trace root minus path integral,
Mm.
you have a system where let's say you put some let's say we divide the Euclidean path integral into space and time.
Mm.
Now you start with a system where you have some spatial boundary conditions. You integrate it from minus infinity to some point to prepare a wave function.
Yes, yes.
And then you prepare the bra like
Yes,
that
correct.
and so on,
Correct.
right? If you think like that, and you think of the doing, I would have thought the boundary conditions along the, since you have told me all the A and B cycles can be
Mm.
thought of like that the boundary condition for every copy along the A and B cycles should be the same, and
Yeah.
should equal that of your
It is puzzling, but I think the answer is that there's an assumption here that the twist fields don't care about boundary conditions, and that's not obvious. In fact, in some sense, it's the twist fields which can shift from being in the NS to the R sector if the boundary condition on this guy and the next guy is not the same. So put it another way, the L calculation, which is the higher-genus one, let's assume we never heard of Cardi, which is a dangerous assumption, but still, and we never heard of twist fields. And we are trying to do this problem, and we do it in higher-genus. What's the rule? Berlindes and Raffas and everybody tells you to sum over to the 2n spin structures for a fermion partition function, and that's the end of the calculus. You can't argue with that. While in the twist field calculation, you have to justify what you're going to do, and it turns out that both. So, in fact, not surprisingly, what Sagar and I found is that if the interval is very small, then treating the spin structures independently is the right thing, to agree with the thermal entropy relation. But if it's very large, then you should have only correlated spin structures on all the copies. And I think this suggests that there's some kind of continuous interpolation. You see, in a higher-genus surface, a boundary condition here and a boundary condition there are just two different things. There's no link between them. But here, with the twist field calculation, there's some kind of rigidity, which is you can take them all the same or you can take them all independent. But those are two extreme choices, and neither of them seems to be completely right. I'll come back to this point at the end.
So in this power series expansion boundary field, which is like this short interval expansion of
Yes.
magnetic wave and
Exactly.
boundary.
Yes, yes.
So there it's like a OPE of the twist fields, in which the twist fields disappear, and you have these primary fields which pop out of the two.
Yeah, but of
and
course,
this is just a product of one point function.
you could say that, but the point is that we know R in terms of theta functions, so there's not. I mean, we don't need that. See, the point is that.
wouldn't that
I'll tell you why OPE isn't enough, because we are on the torus. So torus one-point functions are non-trivial. So it's better to just keep this answer, which is a theta function, and expand the theta function. That's not a hard thing to do.
Sunil, about your boundary conditions and so on, which side do you feel is complicated? The higher-genus side?
I think the higher-genus side is just correct. That's so. If you want my punchline, is that the higher-genus side is always correct. You just can't be wrong. The genus-1 thing with the twist fields seems to have two problems. One is this problem that we just discovered, which is that it seems to have some spurious zeros, and the other is that for fermions specific, well, all this is for fermions. The other is that somehow it doesn't seem to allow you to sum over to the 2n independent spin structures, which is crucial to have a higher-genus free fermion partition function that makes complete sense.
But if you just carefully go through that breaking up of psi into psi and keeping track of the original boundary conditions of the original side,
Yes,
that has to in the end be the same thing.
I agree. And I think in that case what will happen is that we have to assign an arbitrary spin structure to this replicated thing. That means on each torus a different one. Then in the twist field correlator, which is this one, if the boundary condition for one and the other field don't match, this twist field has to somehow be moved from the NS to the R sector in some way. At least this is a suggestion I remember Gabardine gave us 2 years ago, and we still haven't understood how to do it. But I think somebody could do it. I think that the point is that the twist field must depend on the choice of spin structure. It's not very surprising in a way.
Sorry, Sunil, I didn't understand your question. That the higher-genus has to be right, by which I assume you meant the higher-genus where you're summing over all
Yes.
spin structures, right?
Yes.
But I mean, let me just take just genus-1 path integral on the torus. It's still a sensible question what is the answer for this path integral once I've specified the boundary
Of
condition?
course, so that we are not arguing over. The point is that the Ising model is not the theory with any one boundary condition, right?
The Ising model is not. the
This issue
boundary
goes away
condition.
if you say that I'm interested in, let's say, the free fermion theory where the fermion is antiperiodic in space and time. This you can say. It has no spin field, but that theory is a theory, and that for that theory, then there's nothing to discuss about summing over spin structures. There's only the question then whether L is equal to R with that spin structure.
Sorry, but let me just understand. Your original problem is if, let's say, a free fermion.
Okay, so this is my point. My original problem is either a free fermion or it's the Ising model. In my mind, it's the Ising model,
Oh, okay.
not a free fermion.
Okay, so.
But if my original problem was a free fermion, that's why I said with minus boundary conditions, then I have no difficulty comparing these two, where
Yeah.
this has minus boundary conditions on the torus, and this has minus boundary conditions on the entire higher-genus surface.
Okay.
And what you say is completely
Okay,
true.
so sorry, so that's what I was
The
first
problem
thinking.
is that the Ising model truly doesn't have a path integral description. It has 4 path integral descriptions that you are supposed to add.
So,
That is the problem.
okay, now I understand. So,
So you can ask both questions.
So in the Ising model, it's because we do this GSO projection, right?
Yes.
Okay, let me try to make sure I understand. So you have to do the GSO projection, and so you have 3 different things which can contribute, and the 4th one vanishes or whatever.
Yeah.
Okay,
Exactly.
because of 0 modes.
Yeah.
Okay, so
And in
now
the
you
higher
have-
genus, there are 2 to the 2n minus something which contributes.
And so you're saying there is a unique answer for the Ising model on a higher genus surface.
Yes.
This is
That's exactly right.
this, and you're going to get that.
And you better get that, but we
And
don't
clearly.
get that. We don't get that from the other
Okay.
approach. In 2 ways. One is that we are not able, even if L was equal to R, we still wouldn't get it. And L is also not equal to R, which casts a problem on the first question, which is which we don't understand. So there I don't have a theory for it.
And sorry to be dense, but okay, why is it that you're unique? There should be a unique answer for the Ising model, I agree. But why is that answer obviously obtained by just summing over the spin structures? I mean, it seems like a symmetric answer, but I'm just asking, what is the rule? Okay, so I understand that on a torus, you put you project to fermion number 1, whatever sectors in the free fermion.
But which in the path integral language means you have to add different path integrals with different
And
boundary
you have to
conditions.
add different ones.
So the whole construction of the density matrix by gluing path integral becomes now more complicated. And I suspect
Is it okay?
there'll be you see, there'll be gluing of the path integral to itself, there'll be
Yes.
gluing of the path integral to another one with a
Correct.
different boundary condition,
Correct,
cross
correct,
terms.
correct.
And somehow it's in those, I think, that the spin structure issue is raised. But that itself, okay, so that itself would lead one to conclude that, well, L is the correct answer and L happens to match R as long as we fix one spin structure. That was what I thought until a month ago. Till we realized that the matching of L and R itself is a little bit unclear. Though it works there are many checks that it does work, but they seem to all involve small intervals.
But just again, even on the R side, one could logically deduce what the right
Oh, I'm
solution
sure
is.
one can, yes, I'm sure. And I keep saying, I think that's just you take different twist fields.
Right. But one could just sit down and derive.
Absolutely, it should be doable. Yes, yes. No claim that, yeah. This is under the assumption that the twist fields are somehow some fixed twist fields. Yes. So somehow 2 issues have got mixed up. One is the spin structures issue and one is the identity of a higher genus with a genus-n theta function for a special higher genus. So I'd like to focus on the second issue and come back at the end to the first one.
I mean, the complication on this R side again seems like, as you said, on each torus, you had different possible boundary conditions.
Yes, yes.
And then you're making this combined field, which is taking linear
Yes,
combinations.
exactly.
And that seems like
obviously
a complicated thing to do. You have
That's
to think this
exactly
through.
it. Yes, absolutely. I agree with you.
Yes.
Completely agree. So for now, let's do this so-called honest free fermion theory, which has no fancy boundary conditions, and we just pick one spin structure on both sides and stick with it. Okay. So my claim is that the 2 sides seem to agree in a power series in Z12, but don't seem to agree as exact functions.
Even there. Okay.
Yeah, even there. So that's what I want to focus on for the rest of the talk.
Oh, that's
That's more surprising. The other way would simply just, in fact, what I was hoping is that we'll just prove this to be a true identity, and then we sort of go home and say, well, in that case, Takanagi is right to compute this if he wants it in a fixed spin structure, but if we want to sum over spin structures, we need to do better on this side, but this side already tells us the answer. So anyway, we are done, and there's nothing more to discuss. That's what I thought the conclusion of this project was.
Okay.
Part of the reason why we didn't pursue it so hard is that the conclusion was not very surprising. Okay, so this point of spin structure dependence we've just discussed, so that, so this I've already told you. But the interesting thing is that from the higher genus perspective, you can actually find that it does satisfy the thermal entropy relation if you sum over all spin structures. That's a very nice fact, which I am not going to discuss here, but it should be in the paper. Okay. So maybe I'll skip the thermal entropy relation, which is not something that I'm going to use crucially, and if I use, I'll let you know. Instead, let me get down to the calculation of both sides, which I haven't discussed.
So sorry, now this is a free fermion with some
A single free fermion, fixed boundary conditions.
And what are the boundary conditions?
That will be open for the moment, so any alpha beta. But whatever it is in genus-1, it will be just alpha 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 copied and beta 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 copied on the other one. Because that's the only case where you can even claim an identity. Okay. So the starting point is this differential, which is one form on the genus G Riemann surface, on this special replicated surface, which captures the monodromy round through the cut. So if you see here Z1, 2, and then Z is a parameter which or a coordinate of the surface on which omega depends, and there's a set of n of these where k goes from 0, 1, 2, 3 up to n minus 1, and these are the abelian differentials. From these you get the periods by integrating them over A cycles and B cycles, and then once you know these periods, then B times A inverse is omega. That's the way to construct the period matrix omega. Now many say these are fairly, this could be a fairly general statement, but now because of the structure of this, and this comes from old work of Dixon et al. On the orbit fold theories, and then Justin and et al. Actually wrote this expression and so on. So that's fine, and what I have to do is I have to take the kth differential and integrate it from 0 to 1 on the ath surface, or from 0 to tau on the ath surface. So here you see clearly what I said earlier, which is that we take the periods to be round the cycles of the original torus, but on each of the copies. Now not surprisingly, each of these AK is related to the first one A0K by a phase, and likewise for the Bs. And if you do that, the only relevant things are the B0K and A0K, which is take the kth differential but integrate it only on the bottom surface, take the ratio, and then you have to perform this simple sum from k equals 0 to n minus 1, and that's all. So that's the construction. And the way it depends on tau and Z12 is through these periods. So this answers the question, what is omega of the higher genus surface in terms of the physics data, which is the length of the entangling interval, the temperature, and the size of the space.
This answers meaning then from here it's relatively simple to get the full value of beta.
Yeah, it's right here.
Oh, okay.
That's the next line. So once we know omega, we just stick it in the theta function with characteristics alpha and beta. And now this sum is, if you want to sum over spin structures, then this is the true partition function. Now this is a factor which is the so-called determinant factor, which we were able to calculate by a slightly devious route involving Bostonization, which I don't want to go through. But I believe that this is the correct multiplicative factor. And the essential part is this higher genus theta function of these characteristics of omega, which is that omega defined up there.
And sorry, just to ask again about the point that came up earlier. This is the partition function of the bosons on a higher genus surface with this period matrix, and which metric? And which metric?
Yeah. So I claim that with this factor, this is really on this surface.
On this
factor. And at least, if nothing else, it's a good guess, because we'll see that this factor appears in the other calculation also.
I see. And is there a standard answer in a standard metric?
The standard answer in the standard metric is this function times something, this theta function, and all this is called det of del 0 bar, where del 0 bar is
basically
that
this
value.
is like a lure.
Yeah, so det of del 0 bar. So somehow we have convinced ourselves, and I don't know how rigorous that is, that det of del 0 bar is exactly right. One nice thing is, this expression is nicely, after summing over this, it's nicely modular invariant in the higher genus sense. And no, it's actually modular invariant in the tau sense. Tau goes to minus 1 by tau, z goes to z over tau. And for that, this denominator is important because this theta picks up a factor of b over a. This a turns into b, they cancel and you get this back. So that's very, very pretty actually. And this these formulae we got from J.J. and Moon's paper a few years back. Okay, so this is z higher genus. On the other hand, if we do the Takanagi calculation, then you see this is the same factor that's there on the previous page here. And here you see 1 over eta to the n, that's also here. But then this form looks manifestly like a 2-point function on the torus because this is our ordinary Jacobi theta function on the torus. But its argument has some fractions of z1, 2 and you have to take a product of many of them. So on this side it was one theta function in higher genus. On this side it was n of them because it's the 2-point function of n different pairs of crisp fields, so n of them. But it's nice that the eta is the same on both sides, this is the same on both sides, so we can cancel everything. Okay, in this case we don't have guidance on how to sum over spin structures. You could either put the sum there or you could put the sum there. If you put the sum inside, that's independent spin structures on all the copies. If you put it outside, then it's one spin structure on all the copies. And this is what Sagar and I studied and showed that both answers disagree with the thermal entropy relation, but one agrees with it for small intervals and the other agrees with it for large intervals. So in other words, our conclusion was that this naive approach just doesn't lead to a consistent answer. By the way, it's modular invariant whichever way you sum in the genus 1 sense, but it doesn't seem to lead to a physically correct answer. So anyway,
once again, I think the short interval expansion, if I have understood it right, it corresponds to pinching each of these
no.
small.
Pinching what? For this, only
Yeah,
this
what I mean-
goes to this, but the torus is finite.
No, I agree.
Yeah.
So it's like the long degeneration limit.
No,
in which
no degeneration of the torus. It's just short interval. Torus is torus.
Yeah. Torus is torus. I'm saying that suppose you take a genus 2 surface and take the bridge to be, and think of this as two donuts connected by a bridge.
Bridge, yes.
Then you take the bridge to be long.
It's a degeneration,
Yeah.
but it's not the degeneration that it's some combination of the standard degeneration, of course. But it's this one. If I have this and one torus and this and another one, and they are joined like this, then of course this neck can pinch. But no pinching is happening to this or this. Mathematicians like to pinch this.
Yeah. Maybe
So-
that's the degeneration is the wrong word.
Yeah.
But I'm saying that
It is a
the long
degeneration.
bridge
Yes, of course.
is the same as the short cut.
Yes, long bridge between two, yes. But
Yeah.
but the tau of each torus doesn't change at all.
No,
It's a
I
completely
agree.
independent thing. Yes, that's true.
I agree with that.
Yes.
So
Long bridge is the same as it doesn't help us much because now we have diagonalized the problem and done a calculation and that's the answer. Now we know the answer. So there's no problem taking the short interval. I'll do it. I'll show you all the formulae that come out of this. But first, so ignore the spin structure. We've agreed that our discussion doesn't need to take into account spin structures for a while. So ignoring that, so if you can just put the light off again. This is the formula L equals R. This is the higher genus theta function. It has to be normalized by square root of the period, which also contains that dependency on z and tau. But the right side is ordinary Jacobi theta functions, but the arguments have some fractions in them, fractional multiples of the entangling interval, and they are multiplied out. And that comes from the twist fields. So this is the quantity, and so there's a question mark here. Is this equal to this? This is the thing that Samir and I have spent the last 2-3 months discussing. And okay, so I think it's clear. Both depend on Z1, 2 and tau. Here it's explicit. Here it's through omega and through A, through that period matrix omega, and that's it. Okay, so true or false. So now let's look at some take 0 interval size, then the period around the first thing is 1. This omega 0 differential becomes 1. 1 is after all a valid differential on a torus. And so in that case, its integral from 0 to 1 is 1 and 0 to tau is tau. So omega b is tau delta AD, so it's a diagonal period matrix. And in that case, this side becomes the nth power of the corresponding genus-1 Riemann Jacobi theta function, so does the other side, and exactly with all factors. So there's no, that at least determines that nothing has to be normalized again by any chance. Okay. Next, some cute things. If n is odd, number of replicas is odd, and the spin structure is chosen half-half. Now we are choosing one spin structure at a time for this relation. Then of course you know that in half-half, it's an odd spin structure on one torus. Okay. Now in this formula, we have this product, and if n is odd, then k equals 0 is included in this product. But if n is even, then it's not included. But we're taking n odd, so it's included, so then we get theta half-half of 0 as one factor, so the whole thing vanishes. Now, but n is odd, and when n is odd, then the spin structure half-half
Half-half is periodic.
Is also odd in genus, let's say 3. Half-half. But it's not odd in genus 2 or 4. Because you can see why. So, but it turns out, so if n is odd, then the right side vanishes because of the 0 of one of the theta functions, and the left side vanishes because on the left side, the argument is always 0. The Jacobi theta function always has 0. So this always vanishes for odd spin structures. So these are little checks that at least when one vanishes, the other vanishes. And similarly, if you take n to be even number of replicas, you can easily show that neither side vanishes. For the high genus case, it's an even spin structure. For the low genus case, it's still an odd spin structure in each genus, but the argument never goes to 0, so you never get 0. You see that? If n was 2, you get two terms like this, but one has minus 1 by 4z and the other has plus 1 by 4z. You never get 0 times z. Because in this product, when n is 2, it was minus half plus half, not through 0. So, like that. So, these are all nice things. Okay. The next thing we tried was to look at periodicities and modular transformations on both sides. Now, an interesting thing is that you would expect the answer to be periodic under Z12 goes to Z12 plus 1 or tau, which is the entangling interval wrapping around this. But this actually doesn't hold. And in fact, it turns out that you have to take Z12, shift it by n rather than 1 to get periodicity of either side.
So, but in particular, you're saying 0 should have the same, you're just about denying expectation, that 0 should have the same entanglement entropy as the whole thing.
As the whole thing. But of course, not true because of the thermal entropy relation.
Yeah.
So exactly correct. Exactly. So we don't expect that. And in fact, however, the shift by n, is that obvious?
Not to me.
Okay. The shift by n, well, it doesn't leave it invariant, but it leaves it, so shift by Z12 plus n does leave it invariant, but Z12 plus n tau picks up this factor, which is not also a phase, it's a factor.
What did you say about the mistakes in Z12 plus goes to Z12 plus 1? It's like
Either entangling nothing or entangling everything.
Everything.
If it was a pure state, these would be the
In a
same.
pure state, that's the same because of this symmetry on the A and B state, but in a thermal state, it's not.
So when you say, you're saying if Z12 was 0,
As an example of this,
I got you.
so in fact it is not periodic. I need to think more to understand whether it's intuitively obvious that n times it is periodic. Of course we must always remember that here, there's another issue, which is that here we are not working with the entanglement entropy. So the thermal entropy relation, you have to take the limits and then take n goes to 1 in the limit, and it's a little subtle. But okay.
Right, but if it were true for all n,
Yeah.
then it would be true in the
Of
analytical
course,
state.
of
So it
course.
shouldn't be true for all n.
Yeah, absolutely. But now we are actually just thinking mathematically. So if z is shifted by n or n tau, then the higher genus answer respectively is either invariant or it goes to itself up to these kind of factors. Exponential with a tau, exponential with a z. And then we checked So this is easy because, this is hard because you have to perform this on the period matrix omega that we calculated, which involves that cut differential, and then eventually you get this. For R, which is in terms of genus-1 theta functions, it's trivial because you can just take Z in this formula, and shift it by 1 or tau, and you get what you get. This is all in the standard answer on, the standard formulae for theta functions. Here what I'm saying is Z goes to Z plus 1 affects A and omega, and then you have to do a little work. But it was rather pleasing that we got exactly everything right. It's exactly the same. Both sides exactly with the same. So this is periodicity. The next thing to check is the modular transformation in tau. So tau goes to tau plus 1 and minus 1 by tau. And again, it turns out that in this case you get this factor and the spin structures change, which we know actually, right? Under tau goes to tau plus 1. And here also the spin structures from alpha beta go to beta minus alpha technically, and with this factor. And again the identical result also are. So we were very happy. We thought we were almost done once we reached this point. The problem is, if two things have all these properties, you still need to check things like whether there's zeros or something so that you can identify them. So the ratio is constant, and then it has to be, ratio is invariant and has to be constant and all that. But we weren't able to do that. And actually, honestly, till I talked to Samir, I wasn't sure if we were just making some stupid mistake and it was trivially just they were equal. Anyway, so the periodicities are not those of the torus but of its n-fold cover. One strange twist is if n is even, then the periodicities are of its 2n-fold cover. That's just a peculiar thing that happens. Okay. So that's a fact. Now, this motivated us to define a new variable capital Z, which is this interval size divided by the number of replicas. And now you see that if capital Z now shifts by 1, it means small z shifts by n. And so you get this and this, and the same results as before but in a new variable. And now we can look up a book and learn that these are Jacobi forms. In fact, they are weak Jacobi forms. This is exactly the defining relation. So that was very nice. The two standard references on weak or Jacobi forms are Eichler and Zagier's book and Abulkar, Mukhi and Zagier's book. Of which the latter is somewhat better, more readable than typesetting.
So can it be published as a book?
I don't know if it's been published as anything.
Okay.
But at least it's written. There were like 2 years during which it wasn't even written as a paper. But anyway.
I know that Ashok and Atish talked for a long time to write up a book on the n equals 4 case of black holes.
That's
I don't know if
yeah.
that is coming out.
Okay.
This won't be
Interesting. Okay. So the weak Jacobi form, so from these references, these are the properties it satisfies, with some m over here and some k, which are k is the weight, m is the index. So for our case, we see that our quantities satisfy these up to a phase and up to a change in the spin structure, which is not part of this definition. So again, I was very worried, but Samir said, that's no problem. Even ordinary Jacobi theta functions have that fact, and they are called Jacobi forms. Okay, I mean the definition. So this is the problem. This book doesn't mention anything about there being possible changes in any spin structure thing. But the answer for mathematicians is you can always go to a congruent subgroup of SL2Z in which the spin structure doesn't change and the phase isn't there. That's the same way you understand genus-1 theta function. So take it. Anyway, the weight we found n by 2 and the index is this. Again, according to this reference, the weight should be integer, and we were a little baffled because our weight is half integer. But again, I asked Samir and he said, it can be half integer. So, this is, unfortunately, reading Zagier's stuff is very frustrating because they don't tell you everything you need to know. So, this is perfectly consistent. So, sorry to use this k. This k has nothing to do with any k in my talk. This is Zagier's k for the weight of the Jacobi form. And the answer is it's of weight n by 2. We could have told you that because it has n genus-1 theta functions, each of weight half. This we already knew. Not very surprising. Good. So now let's come to the last thing. So one good check is to expand both sides. So for a long time we were trying to do the Q expansion. This was a mistake. It's very hard to do the Q expansion, e to the 2 pi I tau of both sides, because one of the ingredients on the left side is this thing called the B, the period A and B. quantity that was called B0k in general, is the integral from 0 to tau of a form which is a ratio of theta functions. Now the problem with an integral of 0 to tau is that then doing a Q expansion of that is difficult, because the integrand you can do a Q expansion, but now you have to integrate powers of Q from 0 to tau with some function of Z, so that spoils the Q expansion. So actually we found doing the Q expansion extraordinarily hard, and then we realized that we were being silly because you shouldn't do the Q expansion, you should do the Z expansion, and the coefficient in each order is a function of tau, so it's a modular form. So coefficients are modular forms, so you should be able to match them. So it's a lot of data you can match in every power of Z. Zeroth order terms already agree, because I showed you that when Z is 0 it agrees. It turns out that you can organize this such, so the first order turns out 0, second, third and fourth order we calculated and found that they agree on both sides. And in each order, the coefficients of this power series are some Weierstrass P function and derivatives, which are easy to integrate from 0 to 1 and 0 to tau, so you can check that. And right now, what we did is we decided to specialize to 2 replicas and then try to see if we can do this to very high orders just using using the computer, and that's what's going on. But the surprise is the following. Let's just take one particular case with 2 replicas. This is our proposed relation, and you notice that the right side actually has a double 0 when Z is 1 plus tau, because theta 0, 0, which is theta 3, has a 0 at the midpoint of the torus, which is 1 plus tau by 2. So Z is 1 plus tau. Notice that's greater than 1 in particular and also greater than tau. So it's not in the physical region. In fact, capital Z is small z by 2. So small z is 2 plus 2 tau. So it's well outside this torus. Okay. So as I said, capital Z is L by 2L, but physically L is less than L. So the 0 that we are finding lies outside the physical region, since entanglement or any entropy should not vanish for finite intervals in this region. But this vanishes at this point, but the left side doesn't vanish at that point. So this equality certainly doesn't hold if capital Z is 1 plus tau or small z is outside this torus. So at best it could hold inside the torus or in a power series.
So Sunil, can I have a question?
Yeah.
Do you know how to do a large Z expansion?
Large Z expansion, thank you. Nice question. No, actually. I see. Okay, large Z expansion. No. Theta function, ordinary theta functions, is there any way to transform Z to 1 by Z? No. Tau goes to 1 by tau, Z goes to Z over tau, but I don't know how you can make Z large while keeping tau fixed. Off the top of my head, I don't know.
I'm probably missing something, but
Yeah.
didn't you have a periodicity in Z?
Yeah, but the periodicity in Z is larger than the one of this torus, which we just agreed.
Oh, fine, but large Z, then could you use that periodicity?
But this is within that periodicity. So the periodicity in this case is Z goes to Z plus 2 tau.
Good. But
So it's in between the periodicity in this Z and the physical region.
okay, but large Z would start going through this period.
Large Z would actually go through the period. That is also true. Yes, that is correct. So maybe what we want to do is take Z just large enough so that its difference from the boundary of its region is small. That would be interesting.
The middle of this
Yeah,
period.
something like that, yeah. Okay, so that's my last slide, and that's all I basically want to say, which is that the equality we have found does not seem to be exact as an identity among Jacobi forms, which is puzzling, but it seems to be very good as a power series in the entangling interval. So it just leaves everything a little mysterious. The only concluding remarks I want to
Sorry,
make.
but at the level of checks, it could break down even in a power series expansion, right?
It could in principle break down in a, okay, so good.
Like Z to the 5 term or whatever.
Yeah. So that I'm certainly hoping is not the case. That would be very disturbing. It would be better to hope that it's correct order by order, but something non-perturbative in that Z is coming in. I think that's what Samir means when he keeps saying instant terms. And the point is that we are at the stage where at least for 2 replicas, we think we can just generate the whole series.
How much is known of Jacobi theta functions or whatever? They admit a power series expand. Is z equals 0?
Yeah, sure.
Analytic?
Yeah, absolutely.
It's not an essential singularity.
No.
So then there should be a nice Taylor series.
Yeah, there is a nice
Taylor
Taylor
radius of convergence.
Yeah.
And
Looks like the radius of convergence might just be the physical region, and that's in which case.
So in that case, you might think that within the radius of convergence of both, if there's a common region, they should agree.
They should agree.
And maybe outside it.
Yes, exactly.
So
I think that's the most conservative hypothesis. Probably it's the right one.
if that's the case, then for your physics, because
physics we are done.
you converge as mathematics functions.
Yes.
In physics-wise, you are done.
Yeah. But they converge as mathematics functions. Even I think they converge even outside the physical region. That's the point.
The analytic.
The analytic function.
But you don't care. I mean, as a
We don't care.
physicist,
Yeah, exactly.
It's an interesting math
Exactly.
question, but
In fact, in the end, it might, as Shiraz sort of is pointing out, might actually tell us a little more about what is this entanglement we are calculating in a mixed state, in a thermal state. Because it seems to have that property. It's the thermal state which is making these functions not exactly periodic as you might have imagined. At the same time, the entangling interval really should never go above the length of the space. Otherwise you get some funny wrap thing which is not clear what it means. But you're right, we are hoping that it's the maths which has this puzzle but not the physics.
But I mean, what I was asking was, is enough known about Jacobi theta function so you can already say as far as the physics is concerned, you're okay, that is, do these 2 Jacobi theta functions have a radius of...
I'm pretty sure they're just convergent in powers of z within even the region of good. No, I need to check this. The question is whether they are convergent only in the physical region or within the mathematical region where this identity is defined. This I'm not actually sure.
Okay. But even if they were convergent, say, only in the physical region, then there's still the question of checking, I mean, you still have to check or come up with some argument why they would have to converge to the same.
Yeah, so we are hoping to just do the power series on both sides term by term. The beautiful thing is the coefficient of every term is an Eisenstein series. So it's actually coming out very nicely. And last I heard 2 days back from, so this is very up to date sort of. Samir says he has some algorithm where he can make a prediction about Eisenstein series which is now checking. So maybe that will do that should nail it for n equals 2. Which I think is enough, but of course you could argue that it should be done for all n, so I don't know. Anyway, so in the end, as far as the spin structure issue, the twist field computation probably needs to be redone, as Shiraz has been emphasizing. But the fact that these 2 things don't completely agree, I don't know what one should conclude from it, but personally I always felt that the higher-genus method just has to be correct because that's what it is. And all other methods are just ways to calculate the same thing which may work or may not work. And certainly they work when we don't have finite temperature, for example, at 0 temperature they do. Nobody's questioning any of the old calculations. But it makes you rethink a little about this twist field approach. So that's it. Okay, so thank you.
Curiosity, if we had a scalar instead of a fermion, where of course there's no issue of boundary conditions, let's put periodic boundary conditions in its place. Then does it agree?
The answer is that the only attempt with scalar, which is Justin's work followed by J-Jan's work, leads to in fact our answer L exactly.
On both sides.
Squared, because one boson is square of one fermion. So it leads to exactly the square of L, but there is no analog of the calculation R. And the reason is actually very amusing.
For a complex scalar, let's say, there you can have twist fields.
You can have you can take a complex scalar and have twist field. The problem is very interesting. How do you construct twist fields? So let's go back and ask how, because it's not enough to just know their dimension if you want to know the correlator on a torus. It's enough if you want to just know it on a plane. So in the fermion case, you construct the twist fields by bosonizing the fermion and saying that, well, whatever you get, it's some vertex operator e to the I alpha phi, which sends this to, which with this has a fractional OP. this is easy to achieve because the fermion itself in the bosonic language is a vertex operator, and then you know that alpha, this alpha you choose so that this comes out right. That's very easy. In the boson case, how do you construct an operator which, when it multiplies a complex boson, gives you a non-local OPE? In fact, this was a problem that Attic, Dixon and all faced, and they never really resolved it because you just can't.
Z2 overfoldings of the scalar field is an abstract object, right? Or not?
Even for Z2
Z2
using, yeah, probably, yes,
Yeah.
yes. It's a very abstract, you can't write it in terms of something. The trick is for a fermion, you write it in terms of bosons using because in the fermion case, you want the phase to come in the fermion, but that's a shift in its boson because psi is e to the I phi. So the phase of the fermion is a shift of the boson, and that shift is easy to ensure. But the phase of a scalar is not something else, so you don't know how to ensure it.
So you're saying the 2-point function on the torus of this twist field is
Yes, not absolutely. And in fact, I think we've actually at least also
and so on.
we know its dimension.
We don't know.
But I think we've also at least clarified a little the words used in the literature, because even in Jejain's paper and Justin's paper, it looks like they're constructing twist fields for the free boson, but they're really doing the L calculus. They're not doing the R calculus. They may call it anything they like. They're just doing the L calculation. Okay. So one consequence of this, of course, is that if after everything is done, we at least have a proof of Bose-Fermi equivalence, which is that L calculated in the boson and L calculated in the fermion agree. And that's trivial because they always agreed from the 1980s for any period matrix. If you agree to calculate only L for bosons and for fermions, how can they not agree? Because they agree on every period matrix, they surely agree on the replicated surface. So that's also manifest. And finally, I should thank Shiraz for the conversation which started this paper in Guwahati, if you remember. Shiraz and I. Okay.
So this.
And I should thank IIT Guwahati because their wretched bus was 2 hours.
I remember that.
So this A equal to R relation, once again to go back to the long bridge, it reminds me of this, what was it, SO16 cross SO16 string theory, for which you had a Dilaton tadpole, and you have this the relation between the genus-2 partition function and the long bridge limit, and so it was like a Dilaton tadpole square times the propagator.
But that's true here also. In fact, if you pinch this, then it's just the square of this.
So yeah. So
That's actually the test. The first test we performed was zero interval, right? So in zero interval, the period matrix of this becomes diagonal. That's exactly the same as this pinching.
Okay, cool.
So when the period matrix is diagonal, it means that each of the component handles doesn't care about the other one.
But how did they handle how did they take care of the spin structure thing there? I mean,
No, so this is all done with a fixed spin structure. Fixed and same on all.
but when you are computing this two-loop
there.
partition function this issue of
Good point.
Yeah.
Okay, that's interesting. Okay, that I don't know. That I should look up. What is O16 cross O16?
I mean, whatever was the long case of
I see your point. You're saying that they must have also faced the same spin structure
because
issue.
there's a
Good question.
And there were some genus-2 calculations.
there was by local form and some people who established that the genus-2 partition function was related to the Dilaton tadpole square, I think, times the propagator. That this propagator.
So in that case, maybe in their formalism, there's a way to understand the twist fields when the spin structures are different on the two handles.
Yeah.
Because for them, there's no choice in the matter. They have to have that.
Yeah, and I think the longest bridge, of course, is that there's only identity.
Right. That's yes.
But then you can, I presume that you can sort of make an expansion around the length of the bridge, which is what you will do.
What we are doing, absolutely.
And then there will be the other propagators which come in, non-trivial propagators, like the delta.
Right.
The most relevant operator will come next, and then etc. So, and in all these cases, they will have to bother about the spin structure. Well, yes.
Unless there is another pressing question, we can. Thanks.
And Loga.
Oh, Loga, of course.
Sorry.
Sorry, ICTS. Yeah, Loga.
Yes, I just have one more question. Okay. So there was this research that you quoted by Herzog and so on about the first relevant operators correcting the
Yes.
universal answer.
Yes.
Can you use that result to fix how you should sum over spin structure?
Yeah, so we thought of, thank you. So we thought of that. So I think at the, actually that's almost, so the first thing we noticed about Cardy and Herzog's result, they showed this result and then they said, and look, if we look in Takayanagi's calculation of the finite temperature case, then the leading correction is the spin half operator, and that's the lowest operator for the free fermion theory. So that is what baffled us immediately, because it's not the lowest operator for the Ising model, but it is the lowest operator for the free fermion theory. So if you don't sum over spin structures, then of course the lowest operator has spin half. If you do sum over spin structures, then the lowest operator has spin 1/16th, and the answer is also obvious that one of the theta functions, which is not theta 3 but theta 2 or theta 4, starts with q to the 1/16. Just a fact. We know that. So the fact that you need to sum over spin structures to agree with Cardy and Herzog is established right there.
Okay, but you understand this sum on either side, both on the L and the R side?
Yeah, so on the L side, the only sensible way is to sum over all 2 to the 2n spin structures, and I believe that that's also true on the R side, but then you have to, that includes contributions from terms where the different twist fields are associated to different spin structures somehow, and that part we haven't understood. That's what Shiraz was sort of saying in between, that if you do this properly using twist fields, you should be able to do the calculation on the R side, taking into account any spin structure you like, but the twist fields will not be as simple as they are. And just to give you some words, Gabardier's words were you should have your twist fields sometime in the NS and sometimes in the R sector. So this I can completely figure, but I think it's the same idea.
So is the statement that if I just take the name R function that you can have,
Yes.
and if I just expand it, it won't give me the correct answer. It won't give me the answer that Herzog et al. Got.
Yes.
Relevant value for correct.
Well, okay. The point is that as long as z is small, then in fact taking the spin structures independent on each torus is actually correct. So, but I think it agrees in lowest order, but probably will fail in the next order. That's my guess.
Now I'm very confused.
Yeah.
Sorry.
Yeah.
The last part of your talk dealt with a particular spin structure
Yes.
in the.
But he wants now to sum over that. So.
Some of that I understand, but can I just ask? Sorry, look, I
Yeah,
just want
yeah.
to, which is,
Yeah.
if I take your L and R for the second part of your talk with a
Uh-huh.
fixed spin structure
Uh,
and do the large Q expansion, keep the first term a la Cardy,
yes.
do you still get L equals R for that first term?
Yeah. Good. Large Q expansion. Do you get L equals R? So on the R side, the large Q expansion is easy, and we get the answer that Cardy wants. On the left, on the L side, the large Q expansion is a little tricky, but I think we've done it to first order, and I think it agrees with. I mean, it does agree with Cardy, but we don't even know how to go to the next order. So this is leading order in Q. In leading order in Q, they do agree.
Cardy also has only leading.
Yeah, actually he has leading order. I'm doing a different project with one of my students to extend the Cardy thing to the next order,
I got it.
which involves 4-point function.
Sorry, so that was an aside, so now we go back to his summing
Yeah.
out. Yeah. Sorry. Go on, Luca.
No, I don't have a further question. I was just trying to, I didn't understand the answer completely. That is, does the answer depend on how you sum over the spin structure on the
Yes,
R side?
on the R side it does, yes it does.
Okay.
It does because the R side has a product of theta functions, and you can sum before taking that product or after taking that product.
Yes.
And actually when we were writing that paper 2 years ago, we thought one of them was obviously right, and we had everything written until we realized that the thermal entropy relation just doesn't work just doesn't work at one or the other end if you take the spin structure always outside or always inside. And the intuition is that the spin structures across the replicas are correlated if the interval is large and uncorrelated if the interval is small. So for a generic interval, we don't know what they have to do with each other. In both cases, whether uncorrelated or correlated, we can do our calculation of twist fields not worrying about any details. But if it's an intermediate case, then the twist fields probably need to contain some information which they don't have. That's my guess. Okay, thanks Loga. See you.
Okay, let's thank Sunil.